Welcome back. In the last video we were looking at exponential functions, right? And so sometimes we want to be able to graph them, and so to find the graph we maybe want to find the intercepts. So if we find the intercepts of this function, we can find the x-intercepts by certainly just plugging in 0, and we end up getting 3 to the minus 2 minus 4. Okay, and so then 3 to the minus 2 is 1/9 minus 4, and then if I'm doing my math correctly, I get negative 35 over 9 when I simplify it in terms of a fraction. And then finding the other intercept, the y-intercept, I would need to set that was finding the y-intercept. This is finding the x-intercept. So then here I would solve this equation. 0 is equal to 3 to the x minus 2, not 3, minus 4. So then 4 is equal to 3 to the x minus 2. And I need to solve this, but I'm kind of stuck, right? Because I currently don't know of any nice power of 3 that would give me 4 as an output. So I'm stuck, okay? But what I really want to do is I want to get to the exponent, so I need to be able to undo this exponentiation process. That idea of undoing sounds a lot like an inverse function, and that's really what we want to do. Is the exponential function injective? Well, we just said that the exponential function was either increasing or decreasing depending on the value of the base. So yeah, I mean, you think about it, it's always going to be increasing. There's no place where there's going to be two y values that are the same. So then the next question is, what is the inverse function? And that's where mathematics swoops in and says, we're going to define ourselves out of this problem. And that's where logarithms come in. So here's the definition. F of x equals log base b of x is called the logarithmic function. Base b of x, fine. But this is the more important thing here. We have y is equal to log base b of x is the same as b of y, or b to the y is equal to x. So you'll notice that y was the output for the logarithm. It is the input of the exponential. Similarly, x is the input of the logarithm. It switches to the output of the exponential. That's the idea of inverse functions, right? Domain and range switch, inputs and outputs switch. Okay, inverse functions. Okay, so this definition is critical to your success in the course. Now, I think of it as so important that I would say I call it the tattoo, and if I could stand needles, I can't, I would think about putting it in my body, but then I think about, what's it going to look like in a few years, few decades, whatever, and I don't go on with the thought, so I move on. But anyway, remember this, put it on your formula sheet most certainly, and if you get a tattoo, maybe you want to not think about this. Maybe you do. I don't know. But anyway, remember this definition. Some students have told me in the past that they remember this by a circle method. They say, okay, well, you circle the base and say, okay, well, you go to the other side, so you swing to the other side, so b to the y, and then is equal to x, and then you do the same thing on the other side, b to the x, or log base b of x is equal to y. Okay, that's how they remember it. Works for them. Okay, and these two functions, as presented up above, they are inverse functions. Okay, so all we want to be able to do initially here is just get practice with switching between the two forms. Okay, so if we do this, so this one you could probably solve and say, x is going to be 8 and or 6. Rather, it is going to be 6, but let's just practice converting. Okay, so this would be, log base 2 of 64 is equal to x, and eventually we'll learn how to simplify this more, but it does end up being 6. This next one, it would be log base of 5 is equal, or log base 5 of 10 equals x. Next one, log base 1/4, and yeah, we can have a base that's a fraction, it just can't be 1, of 128 is equal to x. And again, this is one that you could solve. And now here, this is the problem that we started with, we'd have log base 3 of 4 is equal to x minus 2, and then add 2, and boom, you're done. And granted, you got to figure out how to evaluate that. Okay? little bit more practice, I want you to pause the video and see if you can now go the other way. So this first row was going from exponential to logarithmic, and now we're going to go from logarithmic to exponential. Pause the video, try them out. Here's what I got for each of these. If you initially switch them all, this is what you get. You could go further. So, for example, you'd say, in the first one, 2/3 is equal to x, and then, 2/7 times 125 is equal to x, and then so on and so forth for each of these. This last one's kind of interesting because you get an output of 0, so then this is just 1 is equal to x plus 1, and then 0 is equal to x. That's kind of interesting. Okay. Now, another thing that you will see later on again, but we want to provide it to you earlier, is that if you ever are asked to evaluate or solve these things, you may want to use these injective properties. The idea is that if you have two bases of the two exponential expressions that have the same base, then just focus on their exponents. Same thing with logarithms. If you have logarithms of the same base, just focus on the inputs. Okay? In essence, drop them. Okay? So here we go. How this applies right now isn't completely clear. We'll see it in a second. If I want to figure out the value of each of these logarithmic expressions, I don't know the value, but I'm going to call it x. So what I'm going to do is now switch it from logarithmic to exponential. Okay, and now you could probably do this in your brain, but I'm going to say this is 3 to the x on the left, and 27 is 3 to the third. Okay, now this is where I use the injective property. So that I have 3's are the same, so then the exponents have to be the same. So then x is equal to 3. Okay. Similarly, this next one, if I set this equal to x, I'd have 2 to the x is equal to 1 over 64. And then this is, let's see, 2 to the x is equal to 1 over 2 to the 6th. And then this is actually equal to 2 to the minus 6. So now I'm at the place where I have same bases, right? And so then set the exponents equal to each other. Oh, that's a terrible color. Won't use that again. X is equal to minus 6. Try the last one. Okay. Here's what I got. So you'll see I had to write both of them in terms of 10 as 10 to a power. So you might have to find common bases for each side, not just one side. And then I got -5/2 as the output. Okay. So a little bit of a different take on exponential expressions. You might need to look at a logarithm, which is the inverse function, and certainly, if nothing else, I mean, this injective property is important, but this had two ideas, converting from logarithmic to exponential, extremely, extremely important. Get this in your notes.